Thank you very much for the nice introduction from Professor Tian Yu. And it's my honor to be invited to give a seminar on the monthly special section of the Microstructure Journal. So my name is Jin Hao Lin. I come from the Department of Physics of Southern University of Science and Technology. And today I'm going to talk about the recent research from my group in doing the atomic study of especially lattice structure and defect in emerging 2D materials. So one of the methods I use is mainly called STEM annual dark field imaging. So it's called scanning transmission electron microscopy at HADF, HAADF. So you can see that it's kind of convergent probe that it can raster the material point by point. And why I'm interested in this kind of technique, because each point it raster of the material has physical meaning. That means it's the capability of the atomic column that can scatter the electrons. Because we are using the annual dark field imaging and using the incoherent elastic scattering electrons. So for a single image, then each pixel has physical meaning. That is, it stands for its atomic number of the scattering atomic columns here. So for example, this is a very nice STEM images, and we can see that it's okay. And we can see that, each spots has bright and dark spots. And we can definitely say that the bright spots has a much more scattering capability than the darker one. So we can interpret this kind of intensity quantitatively so that we can extract the hidden information in the material. And my interest is 2D material. So it is just one atom thick. It really has a very simple structure. So it is the best platform for quantitative intensity analysis. So let me give you a very very easy example to understand. So this is an example that we use the quantitative intensity analysis in a quaternary 2D material. So in this material, we mix 5 elements. That is the vanadium, tungsten, moly, sulfur, and selenium. And by mixing these 5 elements, we can get a monolayer that is 1 molecular layer thick. And we put into the microscope and get a STEM imaging, right? As I told you before, the dark and bright spot here has the physical meaning because it stands for the scattering capability of the atomic columns. So if we write an algorithm to find the peak intensity of each atomic column, and we do a systematic count of each atomic column, then we can get a very nice histogram of the intensity. And this intensity, you can clearly see that it separates into several discrete peaks. So for the cation sites, because we can identify the cation sites, and this is only consists of metals. And the lowest intensity here, stands for the vanadium, because the atomic number of vanadium is the most, among these 5 elements, it is the smallest. So it scatters electron much less than moly. So the middle one is moly. And the brightest one is tungsten because it scatters most of the electrons. So it appears to be very bright. And for the anion size, that becomes a little bit difficult because it consists of 2 atoms. However, 2 atoms just have, several configurations. Like the lowest one is we have 2 sulfur atoms that consists of the lowest darker spot. And then the middle one is 1 selenium replace 1 sulfur and composed of 1 selenium plus 1 sulfur. So that is the middle side here. And then we have 2 selenium as the brightest one in the anion site. So by doing this, we can very, very easy to map out the all the atomic, not only the coordination, but also the atomic elements in each atomic column, so that we don't need to do any elemental analysis like EOS or EDS. We just need to read the intensity of the image of each atomic column so that we can map out its three-dimensional structure by the intensity and also the its chemical identity in each atomic column. Okay, so this is one of the very preliminary example of how we do use the quantitative intensity analysis in 2D material. And if the atoms become really, really large, so by doing, by doing just eye catching or hand counting or label counting, it's a little bit time consuming. So we introduce a machine learning model. That is AI. The AI for science, it's a very hot topic, right? So we introduce an AI model for classifying a lot of atoms in an amorphous monolayer. Okay, so we compare a monolayer amorphous carbon and monolayer nanocrystalline graphene. So we use the quantitative intensity analysis plus the AI machine learning model for the classification. So the machine can tell really where the defect is and what type of defect we are looking at. So by doing this, we can precisely determine the structure of an amorphous monolayer. So in the monolayer amorphous carbon, you can no longer see the grain because nanocrystalline graphene has a well-defined grain structure. That is, it is a loop of the grain boundary that it can separate each grain and with the hexagonal wings inside, so that we can call it a grain boundary. However, if in the amorphous carbon monolayer, we no longer see the grain, we no longer see the grain structure. Instead, we only see a very small nanocrystallites. That is composed of several hexagonal rings embedded in a very distorted string network that is composed of 7 ring members, 7 or 8 member rings here. So you can see that it's a large distorted network rather than the we normally believe as a random network that used to describe the three-dimensional amorphous material. By doing this, we can calculate the amorphous structure very precisely, like we can get the pair correlation function or the radial distribution function in the monolayer amorphous carbon. So that we can do that, we can directly say that it is lack of a long-term periodicity that is confirmed in the RDS function. So by looking, the amorphous material and doing the quantitative intensity analysis atom by atom, we can tell the structural details of an amorphous material. Okay. However, as I told you before, this method, the quantitative intensity analysis is quite powerful. So it not only can identify atoms, it can also identify its structural, the three-dimensional structural information. And this is a work collaborate with Dr. Wu Zhou in UCAS. And we use the quantitative intensity analysis for the three-dimensional reconstruction in a monolayer material. How we do that? We use the quantum scattering theory to calculate the cross-section of a selenium column. Because if a ripple or a wrinkle exists in 2D material, because of there's an inclined angle in the monolayer material, the two selenium atoms will display a little bit, so they will not be very well aligned to each other. Okay, so it can has a very, very small displacement, and this displacement will introduce a phase differences when the electrons go through these two atoms. And this small misalignment of the two atoms will bring a large contrast differences in the intensity because it has a phase differences in the due to the displacement. Okay, and it is determined mainly by the inner collection angle. So we try this. guiding by the theory, we use the MADIF and HARDIF, that is a medium angle, near dark field, and HARDIF, I mean, it's the high angle. So we change the inner angle of the detector, and we clearly see that this effect. We can see that in the middle side here, the selenium column are very bright. And at the two sides, it becomes darker. However, in the HARDIF, if we enlarge the inner collection angle, then such kind of effect will become much more less. So we can, by doing this, by doing the MADIF imaging, we can correlate the displacement of the selenium-2 column with its, probably with its intensity variation. Okay, so we next do the math, do the complicated math to correlate the intensity with the displacement map. So we use two parameters in one image. One is, that is, I previously told you, the intensity, right? The intensity change, I mean, it will change linearly. There has a linear section, linear region versus the displacement. But there's a problem. You can see that at a large displacement around here, around 0.5 angstrom, then the intensity tends to saturate. That means we cannot distinguish how large the displacement between two selenium atoms only by the intensity, because they look the same, right? However, if the two atoms are separate a lot, then the projective shape of the selenium-2 column will become from a round shape and become an ellipse shape, so that we can use this shape change to map and to compensate the intensity saturation, so that we can use this region, we can extract the shape variation from the calculation to construct a linear variation between the displacement and also the intensity with the shape information. Okay, so by doing this, in each column, we can identify how large the two selenium atoms they display with each other. Okay, so this is the displacement vector map that we map from this correlation. And then if we transform this displacement to the tilting angle, then probably we can reconstruct the three-dimensional morphology of a 2D layer just in one single image. Because if we just choose the one reference point at the very flat region here, and we do the path integral, we can extract the three-dimensional information from the path integral and to directly see how the film, how the monolayer deform in the three dimension. So that is how we do that. So we directly do the path integral, and we get this projected image has a three-dimensional morphology like this. And the ripple, the height of the center part here is as high as almost 1 nanometer, which is consistent with the previous study. And we can get a very easy atomic model of the three-dimensional structure of the 2D material just by using one single image, one single stem imaging. Okay, so by doing that, for doing this, we now have a time resolution in the 3D dynamical reconstruction, because we can use the electron beam to directly hit the 2D material and make it vibrate. To vibrate along with the electron excitation. Okay, and if we do the series imaging of using the stem, and we are looking at the material like we are using a hammer to vibrate the material and make it move, make it deform. And we take a snapshot of the images, and then we can reconstruct each frame in this kind of movie so that we can get the three-dimensional reconstruction of a dynamical process of a 2D material. And I think this is the first time in seeing the dynamics of a 2D monolayer that is excited by the electron beam. And in this reference, we also calculate the electron beam has a heating effect in heating, a local heating effect that can affect the three-dimensional dynamics of the 2D material, that it can affect its vibration mode, I mean, of the 2D material like this. Okay, so this is about the quantitative intensity analysis of 2D material that we developed, I mean, during the last 5 years. However, the other side of the big project of the 2D material is we want to investigate a lot of 2D quantum material, we call quantum material. That is, we call the new emerging 2D material. So many examples are like they are emerging in the condensed matter physics area. So it like monolayer vanadium dicyanide, it's a room temperature 2D magnetic system. And also topological edge, topological insulator, like the monolayer tungsten ditelluride. Okay, they are all low-dimensional quantum material that maintain a lot of novel quantum phenomena. So investigating their atomic structure is really important. However, there's a large problem in the investigating the atomic structure of these low-dimensional quantum materials. That is the structural instability. Okay, so most of the quantum monolayer material or low-dimensional quantum material, they suffers from oxidation, deliquescence, hydrocarbon contamination once exposed to ambient condition. Okay, so for conventional TEM, like bulk TEM, I mean, we use the TEM to see the bulk material. Maybe surface contamination is not a big problem because we can still have a lot of signal coming from the inner part of the bulk. However, in 2D material, the bulk is the surface, right? And once the surface gets contaminated, all the efforts in digging out the structure is in vain. So let's give me an example. This is a monolayer topological material called molybdenum ditelluride. Okay, molybdenum ditelluride, once it exfoliated onto the substrate and exposed to air, the color will fade very quickly. And it means that the material gets oxidized very quickly, so that after several hours waiting in the air, the material degrades and you no longer absorb any quantum phenomena in this material, okay? And there's a lot of example, like I give you a lot of example, like titanium, niobium, etc. I mean, a lot of 2D materials are not stable in air. So when I go back to SUSTEC, I want to generalize a protocol that is a universal method to overcome this issue. So that is how I built a very integrated system that is called the Globox interconnected system for unstable 2D material. So we connected from the growth to characterization and to TEM transfer, and then to the modification, cleaning, and finally to the TEM characterization. All these equipment, they are connected inside the inner gas environment. So this is a very special design of equipment, and it's a special design for sensitive monolayer material and also for high resolution and ultra clean structural characterization. So we are very worried or very afraid of the contamination, and we want to avoid any contamination in each experimental stage. We want to avoid the contamination so that we need the whole experiment integrated inside the inner gas environment. Okay, so there's no commercial design, and we designed this system by ourselves. So we now can achieve oxygen and water-free and compatible with the CS corrected stem Globox system. And all the equipment are integrated inside this material system so that we can, I mean, do the whole experiment without exposing to air. Okay, and this system has a lot of extended function because it can connect it to property measurement units like STM, PPMS by the home-built vacuum suit. And also it transferred to the CS stem or TEM by the vacuum transfer holder. so that the sample after growth and fabrication, that they don't need to expose to air. They don't need to expose to ambient condition before loading to any equipment to measure its structure or property functions. Okay, so this is a picture of our system, and it took me about a long time to build it up because we take it part by part. But thanks to a lot of great students, we finally realize it. We have a lot of pattern on building up this kind of system, and we have environment right now. We can realize a semi-automatic TEM sample fabrication inside the system, and the leakage and also water and oxygen environment can control quite low, so that we can completely get rid of the degradation problem of the 2D material. And we also have a lot of special design in the glove box system, like anti-vibration, electrostatic control, and temperature control, and also liquid nitrogen sample loading that is also integrated in this kind of system, so that we can do a lot of special experiments inside our GIS system. Okay, so I'm going to show you some results from this system that we recently achieved. For the first one, that is the monolayer tungsten ditelluride. It's a topological insulator monolayer. Okay. However, when we prepare it in air, and even a very expertise student that only use 30 minutes in preparing such kind of sensitive monolayer, and we control the preparation and also the characterization within an hour, we still see a lot of damage to the material. And this is also the oxidation of the material. Okay, but you can claim that you can still see a little piece of the region that show lattice, right? You can see the lattice here. However, this is not the good results from TEM person, because we know the material is degrading, and this is not the collective large scale information of the material. So this is prepared in air. And when we prepare in the GIS system, we can completely get rid of the oxidation or any contamination that introduced during the fabrication process. So right now we can get a very large intrinsic lattice of the WTU monolayer without any damage. And it is already for large scale analysis of its real space structure. Okay. So only by looking this space, real space structure, we can already see some interesting phenomena, because you can see a little bit distortion in the lattice structure like this. And the distortion is a little bit anisotropic. It is not isotropic like like I showed previously in MOST2 monolayer. Okay, so by mapping out the distortion and also the strain inside the WTE monolayer, we find that the ripple structure is anisotropic in the 1T prime phase. It is very different than the 2H phase graphene or MOS2, because the ripple or wrinkle is isotropic. That means the wrinkle or ripple, they can extend or they can propagate in every direction in this high symmetric lattice. And in 1T prime, because it maintains a very low symmetric lattice phase, so that the lattice or the structural distortion are highly anisotropic. It only prefers certain direction of the distortion. Okay, so that is one very exciting finding of this kind of low symmetry material that can reflect in the real space that the structure also has a lot of anisotropic features. Okay, so very different than the common observed 2D material like MOS2 or WS2 and etc. And let me give you another example that is another very actual sensitive to the dihalide material. And we know that dihalide material always are magnetic, because it consists of a lot of transition metal elements in it. And dihalide material, why there's not much interest in the dihalide material? That is because the dihalide materials are very, very sensitive to water. So by doing this, we make a comparison. In air, if we grow the magnetic dihalide material without any protection, if you put it into the air, in less than 1 minute, the dihalide material will become droplets because of the liquidness. However, if you protect it in hexagonal bond nitride and cover it completely, it can only survive for 3 hours. And finally, it will also turn to a droplet material because it absorbs the water molecules in a very crazy way. However, in GIS system, even we put it in 2 weeks, 14 days, there's no obvious morphology change of this kind of dihalide magnetic materials. So we can do a lot of experiments on this material in investigating its interesting magnetic configuration. Like we can do a TEM, right? We can do a TEM and review its lattice structure. It's a 1T phase dichloride ion. So it maintains a 1T phase, and we can look at its lattice structure, and we can do STM on it and get its very nice atomic images and investigate its stacking. So the stacking looks like it prefers AA stacking. And by 2 layers FECL, we can also do use the MOC spectrum to measure its magnetic properties. So we found that it is an A-type antiferromagnet with a neo temperature around 70 K. Okay, so this is the first time of reporting the synthesis and characterization of a very sensitive 2D magnetic dihalide material. Okay, this is with the GIS. Only with the GIS system we can see this material. And also, a lot of magnetic 2D material are also not stable. For example, the chromium telluride system. So a chromium telluride system, like the chromium 5 telluride 8, I mean, this is a 2D magnetic material. And we grow it as a monolayer, tri-layer, bilayer on top of the tungsten diselenide. Okay, and we found that in our GIS system, even down to bilayer chromium ditelluride, it shows a very superior MOC signal. That means it still maintains the ferromagnetic coupling down to the bilayer level. So you can see a very sharp change. That means the property, the magnetic property maintains quite well in the GIS system. Okay, but if we look at the atomic structure, we also find new things. We find that in the terminated surface of the bilayer, it appears there's a super reconstruction at the terminated interface. That means the terminated interface here, the blue arrow showing it, the intercalation configuration of chromium is different in the bark than in the surface. So in the surface, it will generate, a superlattice that can transfer the electron to the tungsten diselenide substrate. So that we call that this is a dative epitaxy interface. That is the physical origin of why the MOC signal or the long-range ferroelectric coupling, the ferromagnetic coupling can exist down to a bilayer level because it has a dative epitaxy interfacial reconstruction that maintains this structure. Okay, so this is also without the GIS, this material will also degrade very quickly, and we cannot see this kind of phenomenon. And another example I want to show you is the 2D ferroelectric. Okay, so the 2D ferroelectric material like BTO, it's also very sensitive. And in monolayer, it degrades quickly in air. However, in our GIS system, we can synthesize this material down to monolayer, bilayer, and multi-layer. And we found that it has a in-plane ferroelectricity up to the room temperature. And more intriguingly, we found that by tuning the interfacial domain wall, I mean the ferroelectric domain wall, this kind of 2D material, the ferroelectric material, the domain size, the ferroelectric domain size can be tuned by the defects concentration. So this is an example showing that we can artificially increase the concentration of domain walls and then tune the ferroelectric domains from several hundred nanometer down to 5 nanometer, down to 2 nanometer, and to the ultimate limits to 1 nanometer. That means every column has an anti-parallel configuration of the polarization. So that means it changed from the ferroelectric coupling to anti-ferroelectric coupling by tuning the defect concentration in this kind of very unique 2D ferroelectric BTO material. So we found that a unique defect regulation mechanism for controlling the size of the ferroelectric domain in 2D ferroelectric materials, like this. Okay, so this is why we are very proud of the GIT system, that we are continuously producing a lot of good experimental findings that cannot be observed anywhere else, because we have a very unique experiment and have very unique equipment to maintain the whole experiment without exposing to any air. So the whole experiment is quite clean. And I want to show you last two examples that is not 2D material, but a lot of reactive nanomaterial can also work in our system. Like this is a collaborative work with the Fulace group in Wuhan University. Okay, so they synthesize a lot of reactive high entropy nanoparticles. These nanoparticles are so small, and the surface are very reactive. So once it exposed to air, the surface will absorb a lot of hydrocarbon. So we have do a control experiment. If we put this high entropy nanoparticle in air, then for 30 minutes, there's a thick amorphous carbon layer on top, so that we cannot do a very good EDS or EOS or any, imaging for very good signals. However, if we continue, we do the whole experiment in the GIS, we can see there's no carbon deposition on the surface, and the surface are very clean. And we also compare the oxygen content. So by keeping the whole process in the GIS, that we can lower the oxidation level down to about 5% of the nanoparticles. So it's much cleaner and less oxidation for doing the experiment in our GIS system. So by doing this, we use our GIS system to connect it with the E10, the environmental TEM, and we finally review how this reactive nanoparticle form in an in situ environment, because we can get the hydrogen into the column and see how the reaction happens in these high entropy nanoparticles. We found that the nanoparticle keep continually fused and fixed. That is many times during the in situ reaction. Okay, so that means in this kind of high entropy nanoparticles, they keep continuous split and merge, so that the elements can uniformly mix inside the nanoparticle, so that the high entropy nanoparticle can form. Inside the large flow of the hydrogen environment. Okay, so that is we use the GIS connected with the E10 to in situ review to review the formation mechanism of these high entropy nanoparticles. And also, it is also good for the multi-layer sensitive material, like we call the air sensitive heterostructure, because we all know that superconducting material, just as I said before, niobium selenide is really air sensitive. So once you expose to air, you cannot no longer observe superconductivity in the NBSE2 anymore. Okay. However, if we can do it in the GIT system, then we can also not only to keep its intrinsic structure to get the very nice van der Waals interface, that we can see how the NBSE2 are coupling with each other. And we can also preserve the superconducting properties and also the Joseph's junction that can make by this kind of 2D superconducting material. Okay, so we keep the material not degrading by not exposing to any air, so that we can have a very good property and structural correlation between the this kind of sensitive heterostructures. And this is a collaboration with Nanjing University in Professor Li Bo Gao's group with this work. Okay, so another development of the GIBS system is we connected with the cryo-TEM. Okay, for the cryo-TEM, we need nitrogen fabrication, the liquid nitrogen fabrication, that is the low temperature fabrication environment for the sample. Okay, so we have a very special design in our glove box that we can do this. We can use the liquid nitrogen to make the sample fab, and then we can load the sample in a liquid nitrogen environment to the very special TEM called cryo-kiosk. This is a very specialized TEM for the biological application. And this microscope it's a very special one because it equipped with the CS character, so that the spatial resolution of the cryo-TEM can reach as good as the analytical TEM. Okay, so we use this cryo-TEM and with the liquid nitrogen fabrication technique to observe a lot of morph and COF material. We can control the electron dose as low as around 10 electron angstrom per square at the liquid nitrogen temperature, so that we can still see very clear how the organic ligand and how the this kind of carbon organic ligand looks like in the real space. And more recently, we optimized the structural condition and also the TEM. We reach a very extremely threshold limits of the electron sensitive material. That is we call the all organic 2D perovskite. Okay, this material is very sensitive to electron dose. So even above 2 electron per angstrom per square, then we destroy the material. However, we succeed in imaging each organic functional groups, in the cryo-TEM, and show a very nice crystalline structure. And this bright spots stands for one organic group that observed, in the schematic here. Okay, so it's a very low electron dose and only can realize in by the GITS with the cryo-TEM. And this is in collaboration with the Professor Low Camping in PolyU in Hong Kong. They fabricate a sample and we do the sample fab and also the TEM and the cryo-TEM measurement to support their finding. And finally, I want to remind you that a lot of quantum phenomena, they are also electron sensitive, like superconducting state, and also like CDW, charge density wave. Okay, so charge density wave, it's a quantum phenomena that only happen in low temperature. It means the electrons they prefer to form a larger cluster than it's and so that it will form a large periodic lattice distortion in the lattice. So for example, like a very typical quantum material like TAS2, tantalum disulfide. Okay, tantalum disulfide is a quantum material that has several CDW transition. Okay, so in room temperature, it is in the near commensurate CW phase, and at liquid nitrogen temperature, it will undergo the commensurate, the CCDW, I mean commensurate CDW phase. So we put this material into the cryo-TEM, and we can see that the distortion are really reflected in the diffraction and also in the wheel space, because it will generate a lot of new periodicities in the wheel space structure. So by mapping out this kind of superlattice, we can see this superlattice, we can directly extract the distortion of the of these large clusters that we call the defect star. So we can extract the defect star, the center of the defect star of the material in the lattice, and we can do it a very large space wheel space imaging. So first, we examine how these phases are affected by the electron dose. So we can see that as the electron dose accumulates, the CCDW phase, the commensurate CDW phase, will destroy by the electron dose accumulation. And the threshold is about 1,000 electron per Armstrong square. Okay, so the CCDW is also sensitive to the electron dose. And if in a high electron dose, like we typically used to see the atoms in the material, that we no longer can see the CCDW phase in this kind of material. Okay, so we need to keep the electron dose below this threshold. And we keep we get a very large image of the wheel space in the TAS2, and we keep in the safe electron threshold so that we can map the real CDW, the distortion, to map this kind of distortion in the wheel space to see whether we can see they have any unexpected phenomena. And finally, and also luckily, we found the defect star, they also have a stacking fault. Okay, so defect star here, you can see it's a very nice AA type stacking in the defect star. That means the center of the defect star, they are very well aligned with each other. However, in other places, we can see that there also appear to be AB stacking, AB defect star, and also AC stacking, the defect star. That means the center of this defect star in the bulk, they are not aligned together. They have a stacking fault. And this stacking fault is closely related to the band gap with normalization when the quantum the quantum transition happens. Okay, so I need to clarify again, this is not the common stacking fault we observe. This is I think this is the electron structure distortion that leads to lattice distortion in a very pristine lattice, so that we are seeing the stacking fault of the distorted structure. Okay, so I think this is also the first time seeing the three-dimensional CW stacking, the real CW stacking configuration in the real space by using the CS corrected cryo-TEM. And we are doing a lot on this kind of quantum materials. Okay, so finally, I want to conclude my talk that there's a lot of new things to be seen in 2D material, and we are just seeing a very, very small top of an iceberg in the sea. Okay, and the GIS and the new tooth or unique tooth, the GIS, that can hold the whole experiment without exposing to air, that have a very powerful capability to investigate a lot of air-sensitive 2D material, so that we can think more about the structural and property correlation in these low-dimensional quantum materials. Okay, so I would like to thank my collaborator, Dr. Wu Zhou in UCAS, and Panelides and Barbaras and Liu Zheng in Singapore, and many more collaborators that from Wuhan and Nanjing University. And this is the funding source of my work. And this is my group photo. And we have a website of each, the research we present in this talk. And if you are interested, please write me an email that we can communicate much more, after the talk. And we are also having vacancy for postdoc and research professor who is interested in working in 2D material, in situ STEM, and also STEM use. Okay, with that, I would like to thank for your time and thank the audience. Okay, thank you.